Understanding neural networks, architecture and layers. Think of a neural network like a large team of workers solving a big problem together. Each worker, neuron, has a specific task. They take some information, do a small calculation, and pass the result to the next worker. This teamwork allows the system to solve very complex problems. A neural network is made up of layers. Input layer. This is where the data comes in. For example, if you're building a model to recognize handwritten digits, like in a postal system, the input layer might receive pixel values from a scanned image. Hidden layers. These layers are the real workers. They take the input, process it, and send it forward. The more hidden layers a network has, the deeper and more capable it is. Each neuron in these layers is connected to others and performs calculations to transform the input into something more meaningful. For example, one hidden layer might detect edges in an image, while the next one might combine those edges to identify shapes. Output layer. This is the final result. If the task is digit recognition, the output layer might have 10 neurons, one for each digit from 0 to 9, and the one with the highest value tells you the model's prediction. Each connection between neurons has a weight, which is like a dial controlling how important a piece of information is. During training, the neural network adjusts these weights to get better at solving the problem, like a team learning from their mistakes over time. Activation functions and backpropagation. Now imagine if every worker in our neural network just multiplied numbers and passed them on. The entire team would only ever be able to solve simple, straight-line problems. That's where activation functions come in. They let each neuron decide whether or not to pass its result forward and how strongly to do so. Real-world analogy. Think of an activation function like a light switch with a dimmer. If the signal is strong, the light turns on fully, the neuron activates. If it's weak, the light may just glow faintly or not turn on at all. This helps the network make smarter, more flexible decisions. Popular activation functions. Sigmoid, like a smooth on-off switch, great for things that need a yes, no answer. For example, in email spam detection, is it spam, 1, or not, 0? ReLU, rectified linear unit. This function just turns off negative values and keeps positive ones. It's fast and works well in most modern models. It's like saying, if the signal is helpful, use it. If not, ignore it. So how do networks learn? That's where backpropagation comes in. It's the learning engine of the network. Imagine a student taking a math test. After seeing the result, they go back and review what they did wrong on each step. That's what backpropagation does. It checks how wrong the prediction was and then adjusts every connection in the network to improve next time. For example, if your neural network says a picture of a dog is a cat, backpropagation helps trace where the mistake happened. It adjusts weights in the hidden layers. Maybe the shape of the ears was ignored, or the color pattern was misread. Over time, the model learns to recognize dogs and cats correctly, just like a person improves by studying their mistakes. Convolutional neural networks, CNNs, for image processing. When it comes to image recognition, basic neural networks struggle because they treat every pixel the same and don't understand spatial patterns. That's why we use convolutional neural networks, CNNs. They're specialized in processing images by mimicking how we see the world. Real-world example. Imagine you're trying to recognize your friend's face. You don't look at every pixel, you notice patterns like eyes, nose, and mouth. CNNs do the same by using filters that scan parts of the image, detecting features like edges, corners, and textures. Here's how a CNN works. Convolution layer. This is like a camera lens that focuses on small parts of the image to look for patterns. Pooling layer. It shrinks the image to keep only the important features, making the model faster and more efficient. Fully connected layer. This takes the features and makes the final decision, like saying, this is a car, or this is a cat. CNNs are behind many real-life technologies. Face detection in mobile phone, automatic tagging in Facebook photos, self-driving cars detecting pedestrians and road signs, recurrent neural networks, RNNs, for sequential data. While CNNs are good with images, recurrent neural networks, RNNs, are built to handle sequences, data where order matters. Real-world example. Think about predicting the next word in a sentence. If you see the words, "I am feeling very," what comes next? Probably, happy, or tired, right? RNNs remember what came before and use that memory to make better predictions. In an RNN, the network takes input step by step, just like reading a sentence word by word. It passes along a hidden state, like a mental note, that helps it remember past information. This makes it ideal for tasks where context matters. Use cases of RNNs, chatbots and voice assistants, like Siri or Alexa, language translation apps, stock price prediction based on past trends, music or text generation. However, standard RNNs struggle with long sequences, they forget things over time. That's why improved versions like LSTMs, long short-term memory, and GRUS, gated recurrent units, are used. These models remember important information for longer, like remembering the beginning of a story even after many pages. Implementing neural networks in TensorFlow and Keras. Once you understand how neural networks work, the next step is building them, and thankfully, frameworks like TensorFlow and Keras make it easy. Real-world analogy. Think of TensorFlow as the engine of a car. It powers everything behind the scenes. Keras is the dashboard, a simple, user-friendly way to control the engine. Let's say you want to create a neural network to recognize handwritten numbers. Here's how it might look in Keras. From TensorFlow, Keras. Models import sequential from TensorFlow, Keras. Layers import dense model equals sequential, model.add, dense, 128, activation equals, ReLU, input underscore shape equals, 784, model.add, dense, 64, activation equals, ReLU, model.add, dense, 10, activation equals, softmax, model. Compile, optimizer equals, Adam, loss equals, sparse underscore categorical underscore cross entropy, metrics equals, accuracy, model.fit, x underscore train, y underscore train, epochs equals 10. This small script creates a model with 3 layers, uses ReLU and softmax activation functions, trains the model for 10 rounds, epochs, using training data. Thanks to TensorFlow and Keras, building powerful models no longer requires hundreds of lines of code. You can test ideas quickly, tune models easily, and deploy them in real-world applications. Final thought. Neural networks and deep learning have transformed how machines see, understand, and interact with the world. Whether it's recognizing your voice, translating text, diagnosing diseases, or powering self-driving cars, it all starts with the concepts you just learned. Here's what to remember. Neural networks mimic the brain with layers of neurons that learn by adjusting weights. Activation functions give the network flexibility to learn complex patterns. Backpropagation is how networks learn from mistakes. CNNs are experts in handling images, while RNNs are perfect for sequences. Tools like TensorFlow and Keras bring these ideas to life with simple, powerful code. Understanding these concepts is a major step toward building intelligent systems. With practice, you can apply them to real projects and contribute to the future of AI. Would you like the next module in the same format? Great! If you're ready to practice neural networks using TensorFlow and Keras, below is the step-by-step syntax you can try directly in a Jupyter Notebook, Google Colab, or any Python environment. Branch setup. Install TensorFlow. If you're using Google Colab, TensorFlow is already installed. Otherwise, install it using pip install TensorFlow Brain 1. Import libraries. Import TensorFlow as TF from TensorFlow. Keras. Models. Import sequential from TensorFlow. Keras. Layers. Import dense. Flatten from TensorFlow. Keras. Datasets. Import MNIST. Import Matplotlib. PyPlot as PLT in box 2. Load and prepare the dataset, MNIST handwritten digit, x_train, y_train, x_test, y_test, equals MNIST, load_data, hash. Normalize the data, scale pixel values to 0 to 1, x_train equals x_train, 255.0 x_test equals x_test, 255.0. Building construction 3. Build a simple neural network model. Model equals sequential. Flatten, input_shape equals 28, 28, hash flatten 28 by 28 images into 784 dimensional vectors. Dense, 128, activation equals, ReLU, hash hidden layer with ReLU activation dense, 10, activation equals, softmax, hash output layer for 10 classes, digits 0 to 9. 4. Compile the model. Compile, optimizer equals, Adam, loss equals, sparse_categorical_cross entropy, metrics equals, accuracy. 5. Train the model.fit, x_train, y_train, epochs equals 5. 6. Evaluate the model test_loss, test_acc equals model. Evaluate, x_test, y_test, print, f, test accuracy, test_acc, point 2f. 7. Make predictions. Predictions equals model. Predict, x_test, hash. Example, print the prediction and show the image. Import numpy as np index equals 0. Print, predicted label, np, argmax, predictions, index, plt, show, x_test, index, cmap equals, gray, plt, show, checkmark practice checklist. You can practice these steps in Google Colab, free and online, Jupyter Notebook, install via Anaconda or pip, VS Code with a Python environment, any IDE that supports Python.